my presentation? Yes.
Yes,
okay.
you are on.
So thanks very much. It's a pleasure to be welcoming you or joining you in the comfort of your homes, as it is. I'm going to tell you a bit about work we've been doing in my group to sort of include polarization effects by way of polarization corrections in predictions of thermodynamic and other properties. So essentially, this is everyone, I think, in the audience will know this, but just to provide some context. So when you try to model molecules, you have to use these, normally pairwise force fields. The vast majority of force fields out there are pairwise, which means that you only have to monitor interactions between pairs of particles. Now, of course, not all the effects that you want to describe are pairwise interactions. And in particular, I'm highlighting here polarization as a intrinsically non-pairwise effect. Essentially, polarization is a response to the environment that surrounds a given molecule. So how a molecule responds to the surrounding environment. And so that is necessarily a non-pairwise interaction. Now, there's a reason why we use pairwise interactions is to speed things up. Okay, so of course we can use a non-pairwise potential. We call them polarizable force fields, and there's lots of them in the literature, and there's a lot of really interesting developments recently, even trying to make polarizable force fields really fast. But you always have this overhead over pairwise potentials. And so if you use polarizable force fields, you pay a price in terms of computational speed. Okay, now so the alternative, of course, is that you kind of brush polarization under the carpet, right? And you say, well, let's tweak the parameters of the pairwise potential. Let's tweak the Lennard-Jones parameters. Let's tweak the point charges to effectively capture this polarization environment in an approximate mean field way, okay? And, people have done this for ages, and it's been very successful. But of course, if you do that, you necessarily will eventually pay a price in terms of accuracy and realism of the model. Okay, so we have this balance between computational speed and accuracy, as is always present in any kind of model. So I'm going to show you two examples of where we actually suffer a bit from in pairwise fixed charge potentials, where we suffer a bit because of this underestimation or not accounting explicitly for polarization. So first is a dielectric constant prediction. So these are results that I put together of 3 benchmark studies based on 4 different sets of molecular models, just generic models like OPLS or GAF or something like that. Okay, and this is over a very wide range of molecular compounds. Okay, and you can see immediately that if you plot simulation predictions against experiment, there's a big scatter. Okay, dielectric constant is a difficult property to predict, but it's very clear that there's a systematic underestimation of dielectric constant. Okay, so apart from normal shortcomings of the model, there's a systematic deficiency which arguably is arising here because of missing physics, and those missing physics, as I'll show, are the missing polarization contributions. So another example is when you try to predict solvation free energies. I'm plotting here some hydration free energies that we did some years ago. A student of mine calculated, and so even if you look at models that take into account or are good at representing simple compounds like alcohols, amines, ketones, etc. When you mix them together, then it's hit and miss. Okay, you can get it right, you can get it completely wrong. So these compounds on the right are some of them are multifunctional, and you can see that the results are a bit all over the place. And also this happens when you change solvents. So you develop a model for alcohols, and then you pop the alcohol in an alkane solvent. All bets are off. You might get it right, you might get it wrong. Okay, and again, I think a lot of the shortcomings of in this field are due to not accounting for polarization effects. So how do you do that? How do you account for polarization effects without simulating a polarizable force field? So the key is in this slide, I'll show you what happens when a molecule goes from a gas phase where it's isolated, it's suffering no polarization, into a condensed phase environment, which normally I use a liquid here. So a liquid being a state in which the molecule is polarized by surrounding molecules. Okay, and you can follow the notation down here. I won't spend a lot of time here, but basically you can split this step or this process into which I call the experimental path into several steps. So the first is that you take the molecule and you polarize that wave function of the molecule. So you distort the wave function so that it assumes a geometry and electron distribution that is representative of what it would feel in the liquid. Okay, that's what this dipole moment here, mu g goes to mu L. Okay. Then you take into account the interaction of that distorted wave function with the surrounding electrons, right, of the liquid. So you could imagine that it's placed in a bath of electrons of your liquid environment. Okay, that's this epsilon 0 going to epsilon infinity. I'll explain what this is in a second. And then finally, the molecule actually interacts with the other molecules, the other classical entities around them, right? So this is kind of more like a configurational interaction. And this is exactly what we capture when we do an ND simulation. We take a molecule from the gas phase, we put in the liquid, we calculate the classical interactions, okay? But that's not everything. The key concept here is that there are two effects, distortion and electronic effects, that are not captured by classical fixed charge force fields, okay? There's another subtlety which I should mention, is that when you actually do a simulation of a liquid state, you don't actually simulate something in a bath of electrons, you simulate it in vacuum. And so what ends up happening is that you have to scale down the charges respectively to what would be the charges of the real liquid molecule. You use something like a toned down version of the liquid molecule, what we call dipole moment of the model. So the mu m is lower than mu L and higher than mu G. Okay, and it has been shown by Leontiev and Suchevrukov a while ago that in fact this is the effect that's responsible for the fact that we have, for example, for water, all the dipole moments of the classical fixed charge force fields are much lower than what you get from polarizable force fields or from quantum mechanical simulations. Okay. So drilling down into this in a more detail, if you can calculate this distortion term, so this is always a positive energy contribution because you're effectively distorting the wave function of the molecule away from equilibrium. And you can calculate it analytically using some approximation. So this is a famous Berenson expression that was used in the development of SPCE model. And of course, this affects phase change energies like enthalpy of vaporization or solvation free energy, but it doesn't affect the dielectric constant, okay? Because in dielectric constant, you're in the bulk loop. The electronic effects now do affect the dielectric constant quite significantly, as I'll show, because this is now the purely electronic contribution. So the fluctuations of this electron cloud or electron bath are responsible to a non-negligible contribution to the dielectric constant. Okay? And then you have this scaling idea that I mentioned, right? So when you're running a simulation with fixed charge force fields, you're effectively running a simulation with scaled charges because you're trying to capture the potential energy surface of the liquid. That's what you parameterize your model to do. But when you're running simulations and you're trying to predict properties that depend on the dipole moment surface, like the dielectric constant, then you actually should be using the actual liquid phase charges. So you need to unscale these charges to get the correct dielectric constant. Okay. So let me show you in a nutshell how this works for dielectric constant. So this is the expression, the top one is the expression that you normally use to calculate dielectric constant in classical simulations. It's coming from the fluctuations of the instantaneous dipole of the simulation box. Now, the second expression is what you would theoretically use to get the real experimental dielectric constant. So first of all, instead of having one here, you have epsilon infinity. Epsilon infinity is the high frequency dielectric constant, which essentially measures the fluctuations, the response of the electronic degrees of freedom only, okay? And as I said before, that's not captured by definition because this is a classical force field. It's not captured in fixed charge, non-polarizable force fields. So that's the first thing you need to do. The second is that actually, as I said before, this dielectric constant depends on the dipole moment surface of the real liquid. So it should be calculated based on ML and not MM as in the model. So you have to relate them again by the scaling constant K. So if you pop all this together, you get this expression, which is very clean expression to estimate the real dielectric constant from the MD simulations using information about epsilon infinity and K. Okay, how do we actually get that? So epsilon infinity, you can get it from experiment. You can relate that to the index of refraction of each liquid. And then K is the empirical parameter so far. Okay, so we're working on ways of determining this from first principles, but for now, we are fitting K by matching only the dielectric constant of one molecule methanol. Okay, all the rest are predictions. So let me show you how this works. So this is a subset of that graph I showed you before, only for alcohol-containing molecules, so molecules that contain hydroxyl groups. So these are the original predictions of the GAF model, okay? And of course, as I showed, there's a systematic underestimation. So when you actually now include the high-frequency dielectric constant, you see all it does is shifts the curve slightly to the top because it's additive, okay? And you can see already that's almost enough to match the dielectric constant of these low dielectric compounds. Okay, so with low dielectric compounds, epsilon infinity is very important. For high dielectrics, they're not. It's not very important. It's all about the scale. So now, if we apply the scaling, so methanol is one of these. I forget which one of these it is, but we fitted K to match one of these values, and all the rest are predictions from the theory. And you can see that it completely eliminate the systematic deviations from experiment. You still get some scatter, okay, but most of it, the systematic stuff is eliminated. And if you even compare it to a reparameterized model, GAF model that these guys developed, our simple correction approach on the original model is even better than a fully reparameterized model. And I think the reason is because we are capturing this missing physics, whereas reparameterized model just tries to retweak the parameters to get it right, and you eventually don't. And the key important quantity here is the mean sign deviation here in the middle of the table, which essentially measures the bias of the results. And you can see that our scaling factor with this empirical 1.26 scaling is the one that gives you the least systematic deviation compared to experiment. So going back to the original plot, we can now apply the same correction with the same scaling factor, no refitting, nothing like that, just one parameter, and we completely eliminate the systematic deviations. Okay. Now, there's still a lot of scatter, and that comes from the fact that the dielectric constant is difficult to predict using any kind of model. But we're quite happy that we eliminated this systematic deviation. And just to conclude, well, first, before I go to that, we also recently showed that we can apply simple mixing rules with no fitting parameters to predict the dielectric constant of mixtures, ethanol and water in this case, and ethanol benzene over a range of temperatures. So this is only using a single scaling factor fitted to one point, and then everything falls out neatly from this. So just to finalize, I realize I'm running out of time, but just to show you that we can also look at solvation-free energies in this context, in this paradigm of polarization corrections. And now we have to account for the two energy terms, the distortion energy term and the electronic energy term. And they have opposite signs. So for some fluids, I'm going to skip this. This is how we calculate this. For polar fluids, it turns out that both components are very high in magnitude, but they almost have the same magnitude and opposite signs. So they almost cancel out, okay? That's precisely why normal force fields developed for pure liquids under the usual paradigm actually tend to work well, because fortuitously, these two values cancel out. And so you don't really need to account for them. When you have a non-polar molecule solute in any solvent, then the corrections are both zero because the molecule is not polar, okay? But the interesting point is this third one, the green ones, that's when you have a polar molecule in a non-polar solvent. So the distortion term is very small because the solvent is not polar, but the electronic component is still as high as when you have a polar solvent, okay? So the net result is a negative correction that you need to apply to get this right. And just to show you, we apply this to develop a new model for alcohols, and we compare the new model called Polka with for polarization consistent approach, compare it with the trap model. And for the standard properties, it performs a little bit better, but not very different. For the dielectric constant, this is the original trap model down here, and this is the correct trap model in black and our Polka model in red. And of course, both perform much better. That's the same as what I showed you before. But this is the interesting part, is when you have solvation-free energies in different solvents. So this is self-solvation of alcohols in other alcohols. This one is alcohols in alkanes, alkanes in alcohols, and this is alcohols in alkanes. And you can see that when you have this case here of alcohols in alkanes, unless you apply this kind of correction, you will overestimate the solvation free energy, because you're missing this difference in polarization effect when you shift to a different solvent. So essentially, by applying these corrections, we're massively improving the transferability of our force fields. So just to summarize, what we're trying to do is to keep the cheapness, if you will, or the expediency of fixed charge force fields, and try to improve predictions of dielectric constants, solvation free energies, other phase change properties, through applying simple polarization corrections that require essentially no computational effort whatsoever. And so we can remove systematic deviations and improve transferability. And so we're trying to now extend this approach, because what we think is that if we parameterize force fields from scratch using these kind of corrections, you will get much better results overall. Okay. So I'll just finish with this slide to thank my collaborators on the dielectric constant work, Leo and Javier at Strathclyde, also my students Andrew and Cecilia, and my colleague Jose at Aveiro. Thank you very much for your attention.